Welcome to another session of differential geometry class. Today we are going to deal about derivative of a function with respect to a vector. So we are finding derivative of a function with respect to a vector. Definition. First of all, we want to have a function f from u to r. So first of all, we want to define the function. So definition. Let f from u to r be a smooth function where u is an open set in Rn plus 1, and let v belongs to let a vector v belongs to Rpn plus 1, and let p belongs to u also. The derivative of f with respect to the vector v this v is the real number we are denoting it as del v of f is defined as f composition alpha dash of t naught. Now what is this alpha? Alpha is a parameterized curve. Okay, so we want to mention that too, where alpha from I to u is any parameterized curve in u with alpha dot of t naught equal to v. So by definition, if we want to find the derivative of a function with respect to a vector v, means we want to find del v of f, means f composition alpha dash of t naught. Okay, alpha dash of t naught. Now this alpha means is a parameterized curve in u with alpha dot of t naught is equal to v. So even though we are using alpha for defining this derivative with respect to a vector, we can show that this derivative is independent of the choice of alpha. So that is the remark 1. Del vf is independent of the choice of alpha. So how to show it? So by chain rule, what you're having is del v of f is equal to f composition alpha dash of t naught, and that's equal to del f of alpha of t naught dot alpha dot of t naught, that's equal to del f of p dot v, del f of p dot v, because alpha dot of t naught is nothing but v. So this is independent of alpha, right? No alpha terms coming here. So this formula expressing del v of f in terms of the gradient of f shows that the value del v of f is independent of the choice of the parameterized curve alpha. Next remark is remark 2. The function which sends v into del vf. See, we can see that whenever we are finding a vector, we can map that vector to del v of f. So that map is a linear map. From Rpn plus 1 to R. See here, when you are finding your derivative with respect to a vector, means you are taking a v. V belongs to Rpn plus 1. And that v, we can have a mapping from this v to del v of f. So that mapping is a linear map. That is linear map. That is what we want to find. That is del v plus w of some f, right? That should be equal to del vf plus del w of f, and del cv of f is equal to c into del v of f for all v comma w belongs to Rpn plus 1 and c belongs to R. So we want to have we want to prove that this is linear. So consider del v plus w of f. By definition, this is equal to, see here, we have find it out and we have got it as del f of p dot v. So we can use that quantity here. So it should be del f of p dot v plus w, right? Now that's equal to del f of p dot v plus del f of p dot w. So we have proved that. So this is nothing but del v of f plus del w of f. So one part is over. So next we want to prove also del v of some or del cv of f. Del cv of f equal to, using the same definition, del f of p dot, we will get cv, right? Now c is a scalar, so we can have c into del f of p dot v. Now this is nothing but c into del v of f, right? So this is a linear. Therefore, your map, the map v goes to del v of f is a linear one. Is a linear map. Now we can note few things. Note 1. Del v of f depends on the magnitude and direction of v. Magnitude and direction of v. Note 2. The formula del 2v of f is equal to 2 times del v of f expresses the fact that if we move twice as fast through p the observed rate of change of L, the observed rate of change f will be doubled. See, this is the meaning of this. See, whenever your velocity is having twice, then this rate of change of f is getting doubled. Next definition. When norm of v is equal to 1, what will happen? The derivative del vf, del v of f got a special name, is called a directional derivative of f, is called the directional derivative of f at p in the direction v, in the direction of v. So what is directional derivative? So whenever you are finding derivative of a function with respect to a vector and that vector is of magnitude 1, means we will say that it's a directional derivative. Next we want to solve some problems. Question 1. Compute del Vf, where f from Rn plus 1 to R and V belongs to Rpn plus 1, P belongs to Rpn plus 1, P belongs to Rn plus 1 are given by first one, f of x1 x2 is equal to 2x1 square plus 3x2 square, and V is given as 1 0 2 1 and n equal to 1. Second one is given as f of x1 x2 is equal to x1 square minus x2 square, and V is given as 1 1 cos theta sin theta, comma n equal to 1. And third one, f of x1 x2 x3 is equal to x1 x2 x3 square, and V is given as 1 1 1 comma a b c, and n equal to 2. And fourth one, f of q is equal to q dot q, right, and V is equal to PV, comma n arbitrary. So exactly we want to solve 4 problems here. So let me do the first one. The remaining I am leaving for you to work. It's very easy one. So solution. First problem. We know that del V of f is equal to del f of p dot v, right? So here f of x1 x2, here f of x1 x2 is equal to 2x1 square plus 3x2 square. Okay, so we want to find what is del f of x1 x2. Del f of x1 x2 means x1 comma x2, then the derivative. So it will become 4x1, derivative of 2x1 comma 6x2, right? And del f of p, here is given p to be as, see this one p, so it is 1 0, so 1 0 is equal to 1 0 point sh comma, we want to have 4 and here 0, so this is your del f of 1 0. Now we want to find del v of f. So del v of f means del f of 1 0 dot with 1 0 2 1, right? Because the given vector is 1 0 2 1, so we want to have dot with that. So this is equal to del f of 1 0 is this, so 1 0 4 0 dot with 1 0 2 1, and that's equal to, see this part is going to be p, right? Only this part is our vector part, so we want to have dot product, means we should consider like this only, plus this into this plus this into this, so it will become 4 into 2, right? So 4 into 2 plus 0 into 1 will come, right? So we get it as 8. So del v of f is nothing but 8. Next question. So the remaining question I am leaving for you to work, since it is very easy one. So next question is, let U be an open set. U be an open set in Rn plus 1. In Rn plus 1. And let f from U to R be a smooth function. Be a smooth function. Show that if ei is equal to p comma 0 0 extra 0 1 0 extra 0, where p belongs to U and the 1 is in the I plus 1th position or I plus 1th spot here, because 1 2 3 extra up to here will become ei means I plus 1 position, right? This spot. Then del ei of f is equal to dou f by dou xi of p. So we want to show this del ei of f. So derivative of f with respect to the vector ei is this. So solution. First of all, we want to write the formula. So del f of p is equal to p comma dou f by dou x1 at p comma extra dou f by dou xn plus 1 at p. By definition, we have del ei of f is equal to, by definition, del f of p dot ei, right? So this is equal to del f of p we have already written, right? So this is equal to p comma del f by del x1 of p etc. del f by del x n plus 1 of p dot with p comma 0 0 1 0 etc. So it will become, that's equal to only this one term and one term over here will give you a non-zero product, right? So this term should be nothing but dou f by dou xi of p, ith term, right? So we have proved that one. So hope you understood today's class. Today we have discussed only what is derivative of a function with respect to a vector, right? So del v of f is nothing but f composition alpha dash of t naught by definition, and we have found that to be as independent of the choice of alpha, and this can be written as del f of p dot v, and the map, which map v to del v of f is a linear map. Then what is directional derivative? Then how to find this derivative of a function with respect to some vectors, and we have seen one more problem. So hope you understood today's class very well. Thank you for your patient listening.